Hello, good evening, everybody. This is Eric Ranchard. I'm the president of the USOMI, and tonight I have the honor to introduce Nickolas Papanikolaou, who will present a webinar about radiomics. So Nickolas Papanikolaou is working at the Center for the Unknown, which is located in Lisbon at the Champalimaud Foundation Center. And he is head of the Computational Clinical Imaging Group. For the past few years, he has been busy in research, mainly focusing on radiomics for oncology purposes, which is mainly located in body areas like prostate, rectum, breast, lung, etc. Tonight, he will give us more information about the research they are doing to predict outcomes and clinical outcomes of treatment strategies and everything related to this topic. Of course, at the end, there will be a possibility to ask questions. In this platform, you have two ways to do this. There's a Q&A button, which you see in the middle on the below your screen, and there's also a chat function. So if you have questions, and these questions will be discussed at the end of the webinar, then please don't hesitate to send us these questions. The webinar will take about 35 to 40 minutes, so then we will have plenty of time for more questions. So Nickolas, I would like to give the word to you.
Thank you very much, Eric, for introducing me. And I would like also to thank the board of USOMI for inviting me to share my experience on such a hot topic. And good afternoon, everyone. So during the last few years, AI has invaded our lives, influencing significantly the way we interact with smartphones, the way we drive, the way we record our daily activity, and so on and so forth. Due to the recent achievements of machine and deep learning in computer vision domain, a race of applying and adjusting these technologies for medical imaging applications is already in progress. So today we will try to explain in simple terms concepts like radiomics, which is the new discipline that is combining medical imaging with machine and deep learning techniques. So in the next 40 minutes, we will focus on the basic concepts of radiomics, review methods, challenges, and solutions, and finally discuss early clinical results in oncologic imaging with a rather critical eye. Radiologists are generating their diagnosis based on a combination of their training, experience, and individual judgment. They perceive and recognize imaging patterns and infer a diagnosis consistent with those imaging patterns. I guess we all agree that there is an inevitable degree of variability in image interpretation. So in an effort to reduce this variability, alternative avenues like computational imaging or radiomics might be explored, where in principle someone can access far more information comparing to what the naked eye can see, and therefore be more objective. So is everything perfect in computational imaging and radiomics? Certainly not. The most important obstacle at the moment is the fact that the current scanners are designed to produce pretty pictures rather than act as measurement devices. Now, the clinical value of imaging has already been demonstrated. Imaging is considered as an indispensable tool in the era of precision medicine. It provides three-dimensional visualization of the entire tumor. It has been used for many decades in the clinical practice. It is non-invasive, and multiple exams can be performed during the course of the disease due to its non-destructive nature. However, biopsy remains the main source of information when it comes to tumor classification. It's well known that biopsy suffers from sampling errors, and therefore it may not be the best way to study tumor biology, given the fact that a typical feature of cancer is tumor heterogeneity. On the other hand, imaging provides an opportunity to extract important information regarding tumor characteristics in a non-invasive way. However, currently it lacks microscopic resolution. There is a radiation involvement in some of the modalities. It is based on subjective opinions, it's time-consuming, it varies significantly protocol-wise, and therefore suffers from low reproducibility. So there is a clear need to improve reproducibility and diagnostic accuracy, and these are the main driving forces for the development of radiomics, where we are trying to associate imaging features with clinical outcomes. Machine learning methods are used to build, train, and validate models that can aid in the prediction and early stratification of patients, which is at the heart of the precision medicine concept. So let's summarize what radiomics is all about. It's the process of extracting mineable high-dimensional data, mostly from standard of care CT or MRI images or any other kind of digital imaging modalities, data that are used to construct the so-called radiomic signatures, and either alone or in combination with non-imaging data, these signatures might further improve clinical decision-making. The main challenges in radiomics are the limited amount of data available as compared to other fields. Just to give you a small example, in computer vision, the data that are used to train models are in the order of millions. In medical imaging, for the additional reason of expensive data annotation, the relative number is in the order of hundreds. Another challenge is related to the quality of the data, that in principle can be problematic due to the presence of noise, masking the information that we are trying to access. Added to the latter, multiple radiological inputs are necessary to cope with the subjective nature of tasks like segmentation. So radiomics is a data-hungry methodology, and clearly there is a need for sharing data across institutions, not only to increase the number of patients, but also to introduce real-life variants related to differences in the vendors, the protocols, and so on and so forth. New regulations like GDPR poses obstacles to the free and easy sharing of medical data between institutions. And last but not least, a major problem is the limited knowledge on statistical concepts leading to methodological flaws. Some of the most common mistakes that we will focus today are the absence of multiple comparisons correction, the problematic feature selection methods, the incorrect implementation of pre-processing steps, and the leakage of information during training leading to highly over-optimistic results. The previously mentioned problems are responsible for the fact that models are just remembering rules learned during the training process, a situation that leads to poor generalizability. Another obstacle is the difficulty to reproduce the published radiomic signatures due to either the use of proprietary software or non-disclosure of technical details in the publications. As we will mention several times today, overfitting is the #1 enemy in radiomics, and only limited prevention strategies are applied to cope with this problem so far. Finally, it is not uncommon to report the wrong metrics when assessing model performance. Okay, enough with the challenges. Let's start with some definitions. As you probably all know, AI, or artificial intelligence, is the technique that enables machines to mimic human behavior. In particular, machine learning is the science of getting computers to act without being explicitly programmed, while deep learning is a special set of methods that try to emulate the learning approach that human beings are using to gain certain types of knowledge. Deep learning is based on a special category of machine learning algorithms called artificial neural networks. An artificial neural network is a combination of multiple artificial neurons that are comprised of computational units, and they received signals from multiple inputs, and then applying an activation function, they produce an output. It is more than obvious that this design is a simplistic copy of the human neuron. There are two versions of neural networks, the shallow and the deep networks. The shallow is far more simple and it uses a single hidden layer. Apparently, deep neural networks have multiple hidden layers and they are inspired by the stacked neurons configuration found in the human cortex. In particular, the convolutional neural networks have shown to be very efficient handling images as inputs, detecting and classifying different objects. When they firstly introduced back in 2012, they resulted in a breakthrough regarding performance on the ImageNet competition, and it was in 2015 that after continuous improvements in their design, They surpassed human performance on recognizing up to 1,000 different objects. They are trying to mimic the human visual system, where the different cells in the visual cortex are sensitive to small subregions of the input, and those smaller subregions are tiled together to cover the entire visual field. In convolutional neural networks, the design architecture resembles the organization of information in the human visual system. The basic idea is that by sliding a filter like 5 by 5 through several convolutions, the network learns future features that can be low, mid, or high-level representations of the input, and finally, after a fully connected layer, decides on a classification problem. And just to give you an example how these features looks like, they can be edges, textures, patterns, parts of objects, or even objects, spanning from low to high order features. If someone will upload this image on clarify.com, a convolutional neural network will give some probabilities of what is the content of the image. And although the owl is an expert on camouflage, the convolutional neural net is not tricked, and it can recognize it with very high confidence, up to 99.3% probability. In another example from a Google convolutional neural network, for us humans, it is really hard to identify the presence of an animal in this picture, but not for the network. And only if I will spot you the area, you will recognize the head of a leopard. Now, the basic difference between machine and deep learning is that in deep learning, data-oriented feature extraction is taking place automatically, and it's integrated to the classification process. Now, let's review the basic components of a radiomics pipeline. A radiomics pipeline comprises multiple phases, including image acquisition, pre-processing, segmentation, feature extraction, analysis, and reporting of the results. Protocol optimization is the basis for a robust outcome of the pipeline. And since the principle of garbage in, garbage out applies here, it is mandatory that the clinical scientist needs to develop and optimize image acquisition protocols and calculate quality-related factors like reproducibility, stability, precision, and others, since we are talking about a quantitative method. In case we have done a good job in the image acquisition phase, the pre-processing can be minimal. Otherwise, we need to explore filtering methods to improve the quality of our data and reduce artifacts, and especially in MRI, we need to correct signal heterogeneities that are related to many different technical factors, mostly RF coils characteristics. A critical part and the potential bottleneck of the workflow is related to lesion segmentation. And there are various methodologies that are already available with pros and cons for each one. But the target here is to provide with an accurate method that can result in minimal human interaction. Following the definition of our volume of interest, the next step is to extract imaging features from that volume. In general, features can be classified into two categories. Engineered or handcrafted features are often based on intensity, shape, texture, wavelets, and others, while in the second category, we have the deep features that can be learned automatically from the data. These features are included in the neural net's hidden layers. We don't have any control on the generation and selection of those features, and that's why deep learning methods are considered as black boxes. Handcrafted radiomic features can be further classified into agnostic and semantic. Semantic features are commonly used by radiologists to describe lesions, and these include diameter, volume, morphology, and others, while agnostic features are mathematically extracted quantitative descriptors, which are generally not part of the radiological lexicon. So what is texture? Texture is a regular repetition of an element or a pattern on a surface with characteristics of brightness, color, size, and shape. The vast amount of agnostic features are based on texture analysis, and there are many variations, with the Haralick method to be the most popular one clinically wise. First-order features estimate properties of individual voxel values, signal intensities, ignoring the spatial interaction between neighboring voxels. A second layer of information is related to the shape of the lesion or volume of interest, and we can quantify up to 13 different shape-related features. Co-occurrence matrices provide second-order features that quantify relationships between pairs of voxels. They are usually defined according to a given spatial direction and a given distance between the pairs of voxels. Let's see a practical example. Let's consider the red square and try to fill it with a gray level co-occurrence matrix where we should identify how many pairs of 15s we have. It's 2, right? Then we have a pair of 15 and 16. We don't have any pairs of 15s and 17s, the same for 15s and 18s, one pair of 15 and 19, and so on and so forth. It is important to understand that all these calculations can be done with different distances and different degrees in space. And in our example, I have used 1 pixel as distance and 0 degrees as an angle, which means I examined the relationships in the horizontal axis. Apart from GLCM, there are many different versions of texture matrices, like the gray level run length matrix, the gray level size zone matrix, and others. A very comprehensive open source library that I highly recommend you is the Radiomics, that offers feature extraction not only on original images, but also on filtered ones like Laplacian of Gaussian, wavelets, squares, and others. This is a comparative example of one of the texture features, which is entropy, and it is much higher in the malignant infiltrative ductal carcinoma in the breast, comparing to a benign fibroadenoma. The core of radiomic workflow is the analysis part, which is the most interesting and the most challenging one. In machine learning, methods can be divided into supervised and unsupervised. In supervised learning, we must provide labeled data during the training. In other words, the algorithm needs to know what is the ground truth for each patient. On the contrary, unsupervised learning is not making use of the labels, rather than it tries to reveal associations between different types of data. This is an example of a hierarchical cluster analysis that was done using 15 texture features extracted from a B1000 diffusion images obtained on patients with pancreatic cancer and normal controls. And those selected features provided very high discrimination accuracy between controls and patients. During the clustering of the data, the algorithm was agnostic to whether data comes from a patient or a normal control. And as you may appreciate, there are 2 major clusters, one on the right that is populated exclusively from patients, and another one on the left that basically is populated by normal controls with just one misclassified patient. So what are the most common problems that someone can solve with machine learning? It can be classification problems, is it A or B, regression problems, how much or how many, clustering problems, how is it organized, what belongs to each other, associations and correlations, what happens together, what changes together, and anomaly detection. Is this very different to the normal distribution? So as an initial step, someone has to identify the worth of each feature individually over the 2 or more classes, and that is the so-called univariate analysis. When performing univariate analysis, having a large number of candidate features to check their predictive power against the ground truth variable, there is always a risk of identifying features that provide significant differences between classes by chance, and therefore always use multiple comparisons correction methods. This is just an example that serves to illustrate the truth of what was said in the previous slide. I have generated a random data set with 100 samples and 500 imaging features for each sample, resembling a radiomics problem. By performing univariate analysis with a t-test, I was able to identify several imaging features that were capable of providing statistically significant differences between the 2 classes. But wait a moment, how is that possible? Since I used random data without any information. Well, it happens by chance, since the number of candidate features are far more than the number of samples, which is always the case in radiomics problems. So by correcting for multiple comparisons using, for example, a Benjamini-Hockenberg test, my results are as expected, where there is not a single feature that could provide statistically significant differences between the 2 classes. Now, here is a clinical example. In 26 patients with rectal cancer, We identified 12 radiomic features out of 986 that were capable of discriminating responders from non-responders after chemoradiation therapy. But when applying multiple comparisons correction, none of them provided values lower than 0.05. So it's really important to be able to safeguard yourself, not to be exposed to methodological mistakes. The next step is to perform multivariate analysis, or in other words, modeling. What is a model? It's a simplification of something far more complex. In particular, a machine learning model or algorithm tries to identify structure on the data. It constructs rules to simplify the complexity of the data and identifies relationships that can be used to learn how to perform a specific task. In machine learning, training a predictive model means finding a function which maps a set of values x to a value y. We can calculate how well such a model is doing by comparing the predicted values with the true values for y. Classification problems are very common in radiomics, and they are trying to predict the ground truth or the label. For example, if a specific lesion with such and such imaging features is benign or malignant, aggressive or non-aggressive, responding or not responding to treatment. After we trained our model, we need to assess its performance on unknown data. This is done through the validation process by means of different metrics, depending, of course, on the problem. A major challenge here is to build models that are robust and can perform equally well on unknown prospective data. The correct validation implementation is vital to avoid over-optimistic expectations. Now, training error is the error that is calculated on training data, and it's useless. You should never even report it. What is important here is the test error, and that is the error measured on a data set that was held out from the training process, and it's called the test data set. Most of the problems arise from imperfect isolation of the test set from the algorithm, especially when methods like cross-validation are used. Ideally, we need to use two data sets, one for training and one for testing. And the test set should be a separate external data set. But since that is quite difficult, and in most of the cases we can't have external data, when we have the luxury of having a rather big data set, we can split it into two chunks, for example, 80% for training and 20% for testing. That is the split validation method. But what about when you don't have that many data? We could use another very popular method, which is called k-fold cross-validation. In that case, we divide the whole data set into k-folds, and we use k-1 for training and 1 for testing. And we repeat that for k times. So we build k models and we average their performance. Cross-validation is a perfect way to make full use of our data without leaking information into the training phase. Cross-validation is generally believed to be a very accurate and much more accurate method than the simple split validation. Split validation measures performance based only one random sample of the data, whereas cross-validation makes use of all the data. Think about it in this way. The holdout from a split validation is simply one of the k-folds of a cross-validation. A subtype of k-fold cross-validation is leave one out, where the k equals to the number of patients or samples. And then you have also the bootstrapping validation, where we build models several times by replacing specific data. The latter is a quite popular method in medical imaging since it provides more accurate estimates in the presence of small data. In radiomics, as in other omics applications, we are dealing with a problem called P far greater than N, which means that the number of predictors are far greater than the number of samples. And this is a problem that is related to the so-called curse of dimensionality. So a reasonable question here is how many features someone should recruit in order to build their models. If you use very few features, you might underfit your model. If you use too many features, you may overfit your model. What is important is to identify the proper amount of bias and variance of your model that minimizes the test error. Irrelevant features might contribute very little to the predictive models and can actually degrade the prediction. In any machine learning problem, and especially in radiomics, there is a process of selecting a subset of relevant and useful features that will finally comprise the radiomic signature. A nice analog is the guy that tries to identify among many stones which are the golden ones. And that is the essence of feature selection. So these are three graphs showing three different possibilities that might result after training our model. In case we don't use too much information, very low number of features, for example, probably we will not be able to find a good model and we will underfit the data. On the other extreme is overfitting, where the model learns too many information that probably are unique to the training set, and that is the reason why it fails to perform equally well on unknown data. A well-fitted model is a balance between bias and variance. Feature selection has many benefits when done properly, with the most important being the minimization of overfitting. At the top of that, of course, feature selection can facilitate data visualization and data comprehension. It may reduce the measurement and storage requirements, and it can reduce training and utilization times. There are various methods used for feature selection, starting with the filtered methods, where we rank features according to their worth by recruiting different statistical tests like Pearson's correlation, Wilcoxon t-test, and others. Another type of feature selection method are the wrapper methods, where we use different groups of features by applying forward selection, which is starting from one feature and gradually adding more till the performance of the model doesn't further improve, or backward elimination, where we start with all features and gradually removing some of them till the performance of the model starts to drop. Finally, we have more sophisticated techniques that are called embedded, and they are usually a combination of filtered and wrapper methods like the lasso or the elastic net. So one potential way to do feature selection is to start by removing features with zero or near zero variance across your patients, and then remove highly correlated features that carries the same information, remove unstable features by calculating stability based either on test-retest approach, that is the temporal stability, or by asking two or more radiologists to provide segmentations of the same patients, and by applying statistical tests like the interclass correlation. For example, you can check which of the features doesn't change their values significantly. Then in case we do univariate analysis, we need to correct for multiple comparisons, or we can skip that in case we go for multivariate analysis, where feature selection methods like recursive feature elimination or minimum redundancy, maximum relevance can be applied to slim down our radiomic signature. This is an example of a correlation matrix where features with red and blue colors are highly correlated and therefore removed from further analysis. Now, one of the most common mistakes is cherry-picking features prior cross-validation. That will result in optimistic and wrong estimates of the performance, since there is a leakage of the ground truth during the feature selection process. The proper way to do this is in a nested approach, where features are selected in an iterative way for each training fold. Just to give you some proofs, again, I'm using a data set that I generated randomly without any real data, and by selecting the best 10 features prior my cross-validation operator, I can achieve a classification accuracy of 92%. So let's have a look on a clinical example. 52 patients with multiple myeloma, diffusion of the lumbar spine was performed, and 956 radiomic features were extracted from ADC maps. The ground truth here was cytogenetic status, low or high. When picking the 5 most informative features before training my model, I'm calculating an exciting accuracy of 74%. But I have already exposed the labels of all the data to the model. Now, if I'm going to do it again, but now in a correct way, having the feature selection for each k-fold, I get my realistic accuracy of only 38%. So this simple mistake is the reason why there are many discrepancies between the performance that someone reports from cross-validation operators and the actual performance on unknown data. A common mistake is to focus on the model rather than the data. And you must be very cautious when dealing with models that produces very high area under the curves, since most probably those models are over-optimistic due to methodological mistakes. In addition, there is a confusion between correlation and causation. Another question has to do with the number of patients that we should recruit to develop and validate our models. In general, deep learning methods are increasing their performance with more data, while in traditional machine learning, there is a saturation effect much earlier. As a rule of thumb, you must remember that for every feature that your final model uses, you need to include 10 to 15 cases. So for a 5-feature model, you need at least 50 to 75 cases, or for a 15-feature model, you need to have at least 150 cases. Apparently, discovery and validation of radiomic signatures cannot be based on a single-center approach. We need to collaborate, share, and learn. And for that reason, our group at Champalimaud Foundation has developed an international radiomics network, which mission is to discover radiomic signatures that will make a clinical impact to the oncologic patient, improving clinical decision-making by the power of AI methods. According to my personal opinion, we have already reached the peak of the radiomics hype, and now it's the most critical phase to identify the realistic potential of these methods in order to operationalize them into the clinical environment. Moving to some clinical applications, everything started back in 2007, where Aaron Segal and his group posed the question whether imaging features could predict gene expressions. And they managed to show that 28 imaging features could reconstruct up to 78% of a liver cancer gene expression profile. Additionally, it has been demonstrated that features such as tumor image heterogeneity were associated with genomic heterogeneity and were correlated with increased treatment resistance and metastatic propensity. In another study of lung cancer patients, the authors investigated the association between radiomic features and the tumor histological subtypes. Furthermore, in order to predict histological subtypes, they employed machine learning methods like random forests, naive Bayes, or k-nearest neighbors, and independently evaluated their prediction performance, showing that imaging features could be used to classify patients according to their tumor subtypes even before biopsy. In another study in breast cancer, features were extracted from MR mammography in the arterial phase of the dynamic experiment were capable of predicting different molecular subtypes. Some unpublished data from our group where we tried to predict the pathologic complete response before initiating neoadjuvant treatment, and several wavelets, as you may appreciate, were provided area under the curve around 0.77, which is a quite good performance. In this heat map, there are 4 clusters identified in an unsupervised manner. And as you may appreciate, there are at least 2 clusters, the first and the last one, that are mostly populated by complete responders, while these two clusters are mainly populated by non-responders. Within the plethora of publications on radiomics, someone can realize that many of them, either they don't report properly the methods that were followed, or they report methods that are well known, especially in other disciplines, to be unreliable and responsible for over-optimistic results. One example is this paper where, apart from the low number of patients, several methodological aspects can be heavily criticized in a way that the reported results cannot be validated or reproduced by any means. Most of these textual features identified as capable to discriminate responders from non-responders wouldn't survive after multiple comparisons correction, given the high number of initial features used and the marginal p-values obtained in non-corrected t-tests. In the prostate cancer area, there are papers that are trying to assess the performance of radiomics in the discrimination of clinically significant from non-significant disease. For example, in this paper, the authors report excellent performance, reaching 99.9% area under the curve. But wait a minute, that would be the end of radiologists. If we have such models, then why do we need them? Well, by looking more thoroughly to the methods, the authors aren't providing clear data regarding the way they have implemented feature selection. And here is the responsibility of the journal reviewers to demand clarity on these issues. What happened here, most probably, and I can only speculate, is that the labels of the testing set were leaked during the feature selection, and that's why they are reporting such extraordinary performance. Now, in another paper in the same topic, the authors reach very different conclusions, presenting machine learning to be equivalent to the traditional approaches like measuring a single ADC value. And due to the correct methods followed, which is the nested approach when doing feature selection, their reported performance was far more realistic. In the field of multiple myeloma, again, unpublished data from our group, there are 113 patients that are participating in an ongoing study where several features were capable of discriminating normal from abnormal patterns with a relatively high area under the curve reaching 0.9. Most of them were related to histogram metrics, and in other words, ADC values that apparently were different between abnormal patterns, including diffuse and focal, and normal patterns. So our take-home messages here is that there is a clear association between imaging phenotypes and histology. Radiomics have the power to provide prognostic information regarding tumor aggressiveness, metastatic potential, overall survival, and other clinical outcomes. More research is still needed to provide insights on the correlation between the underlying biological processes and the perceived image datasets. Last but not least, be critical to over-optimistic results and ask from experts help when experimenting in unknown territories. And there is a very nice word in my language, which is called symbiosis, which basically describes the relationship that will and should be developed in the future between radiologists and machines. After all, AI is here to empower radiologists rather than to replace them. And finally, since this is a teamwork, I want to acknowledge my group and all the radiologists provided us with valuable input and help. And I want to thank you very much for your attention and wish you Merry Christmas to all of you.
Thank you very much, Nickolas, for this very, very interesting and complete overview of radiomics. It is a very, let's say, interesting topic, and for radiologists, for the radiologists among us, it opens a completely new insight on the way data can be analyzed, data coming from images, of course. At this moment, I do see a question here. From Emmanuel Androulidakis, he says, can you tell us if there are any clinical applications currently working in clinical practice?
Well, most of the applications at the moment are limited into the detection of pathologic tissue versus normal tissue. More sophisticated and clinical questions like treatment response and most importantly, correlation with clinical outcomes like overall survival are still pending. And the main reason why is exactly the lack of comprehensive data to support this kind of model development. So I believe that in the near future, and especially when big networks of hospitals and organizations will be formed, having access to vast numbers of data, that will definitely be the solution, and more clinical models will be applied into the clinical practice.
Yes, so this is certainly something that is, let's say, popping up in all lectures. That is the lack of data and the efforts that are needed to prepare those data, to curate data, to label data, etc. So this seems a very huge effort, and I also think this is one of the reasons why the biobanks are playing such a tremendous role. How do you think this will be facilitated in the future? Is there sufficient support from, for example, the European Union, or what other kind of support do you see?
Well, there is already ongoing funding schemes for big data and biobanks and machine learning and deep learning, mainly from EU. So I believe that in the future, and especially with the pressure that the healthcare systems are facing, these type of infrastructure will be available and further exploited in order to produce clinically important models.
Yes, and I think that not only image biobanks should be available, but probably also the genomic biobanks, so that this information can be linked, of course. And then we talk about radiogenomics, right?
Exactly. Something that I missed to mention and to stress is the fact that imaging can give solutions to a certain extent, but sometimes you really need to add additional layers of information coming from genomics, from metabolomics, from proteomics, or even from clinical variables. So definitely we need to invest on big biobanks that are diverse and offer different kind of data for these kind of tasks.
Yes, exactly. I can see a question here from Yanis Pandonis, and he says, are there any industry-related partners involved in the radiomics initiative, like the pharma industry?
Well, I'm not aware of specific examples, but I can only speculate that this is very reasonable, because another very important area currently for research is drug discovery. And there, radiomics also might prove quite helpful. But this is the beginning, actually. So we need to be cautious. We need to put our feet on the ground and not fly. And as I showed, the radiomics hype curve is already at the maximum. But unfortunately, very many papers have been published during the last 3 or 4 years, but most of them are highly problematic. So we definitely need to be realistic and to try to do it in a lege artis way.
Yes, nevertheless, you can see a movement in the market where radiomics are being introduced for trials. And then you also see, for example, the partnerships that are being made between vendors and the pharmaceuticals, like GE and Roche now have an agreement. So I do think that there will be a future for this kind of developments.
Actually, I have a question concerning the vendors, because now there are some vendors like Olea that will work at that introduced radiomics. But do you believe that radiomics now is all ready to work on individual cases, or for now it remains more something that we should do for the studies for the clinical trials, but not for individual cases?
Well, if I'm not mistaken, you are talking about texture analysis in particular.
Yes, for example.
Right. Well, I have seen many papers using texture analysis, but missing the multiple comparisons correction. And therefore, there is a lot of criticism against this kind of applications. But if you do it in a proper way, definitely there is lots of space to develop new things and to assess in a more objective and quantitative way problems that cannot be solved with the current methods.
I have a question from Vasilis Katsaros, and he says, what about the already automated segmentations and parcellations for brain pathologies, which already have FDA and CE approval?
Yes, exactly. Well, one active area of research is in the segmentation field. There, I think that we are far more advanced comparing to clinical related algorithms and methods. And although in the beginning there was quite a lot of criticism, especially from FDA for deep learning type of approaches, now more and more FDA is becoming more flexible and approves this kind of deep learning methods, which are far better in terms of performance for segmentation reasons. And the main reason why is that on the segmentation problems, even with a small number of patients, someone can train efficiently these kind of networks, since the problem there is on a pixel basis. So you have thousands or even hundreds of thousands of pixels if you consider even 100 patients. So yes, I agree, Vasilis, segmentation is far more advanced and will be much faster integrated into the clinical routine.
We have a question from Roberto Barone. He says, hello, why in your opinion are there so many papers without p-value adjustment or with problems in feature selection on the whole data set?
I believe that has to do with improper training of radiologists into statistical methods. And this is one of the fields that in the near future radiologists should focus and adapt their training curriculum to include other kind of disciplines like statistics and machine learning. So I believe it's just ignorance of what should be the proper way to do this kind of analysis.
Yes, I think you made a very important remark here. I agree with you that the further training and adaptation of the current training is very crucial. Of course, I'm not saying that radiologists should become computer scientists, but there needs to be a more thorough knowledge of the technologies that are being used currently. Further question that I have, oh no, I see a question here about, yes, the costs that are involved. What about the cost? Could you give us some more information about that?
Well, I'm not into commercializing business of these kind of models. I'm just developing them for pure research purposes. But I believe that if you have this kind of algorithms and if they are properly trained and validated, they should participate on healthcare cost reductions, since the clinical decision-making will be far more accurate, and therefore treatment costs can go down. Now, if you are asking about the cost of a user of this kind of services, I guess in the market there are companies that are offering this kind of services on a per patient basis, charging something like €1 per patient. So it's really cost effective.
Mm-hmm. Well, I think this is currently one of the major issues also with the AI algorithms. This is everybody's looking for the right business model, and it's also a good question that I see here, which is quite relevant. So will it be accessible for everybody? Will there be, if the software and the applications are becoming more expensive, who is going to take care of the financial part, the funding? Where will it be available? Will it be not available in some parts, etc.? So this is a quite relevant issue, I think.
Well, I can only speculate again, but I believe that this kind of technology will be far more accessible due to the far lower cost per patient. I mean, imagine countries where they were struggling to install decent MRI scanners. Or, for example, another big contribution of this kind of algorithms would be to provide some kind of initial evaluation in cases where there is a shortage of radiologists. Mm-hmm. I mean, remote areas or countries where there are not so many radiologists definitely can benefit from this kind of approaches.
Yes. I also have a question for you, Nickolas. Regarding the value of standards, developing standards in radiomics. I can imagine that there are some differences between, you know, depending on in which location the data are generated. And so, I mean, the results might be variable from center to center or maybe between different machines. So how is this being taken care of, because the results might be highly variable, or as you have with the DWI results, for example, diffusion weighted imaging, the ADC values are also variable from machine to machine. So how is this being taken care of?
Exactly. You touched a very sensitive topic, and this is protocol standardization and how the models can be affected not only by different vendors, but also by changing slightly the value of a single parameter. Just this, a little bit before I start the webinar, my collaborator showed me a graph where more than 80% of the features were already become unstable when changing the TE from 80 to 90 milliseconds. So clearly there is a big issue here when it comes to standardization. And my gut feeling here, although we are trying to train and validate and develop robust models, my gut feeling here says that most probably the models will be developed for specific vendors, even for specific protocols. Mm-hmm. Exactly because of these sensitivity. I mean, there are many examples. For example, when the vendor is upgrading the software, it is not unexpected the fact that previously trained models on previous data might collapse. So there is a big sensitivity on the standardization issue.
Yes, that's very interesting. I have another question from Alexandros Kalifatidis. He says, which exams work better so far with the data selection? Is it what modality? Is it CT, MRI, PET?
Okay.
And for which anatomic parts or for which pathology?
Right. I think the most popular application at the moment is the lung cancer based on CT data. CT as a quantitative method that produces Hounsfield units, basically, it is far more adequate and suitable for this kind of texture analysis and radiomics modeling. In MR, it's a little bit more difficult since the signal intensities on MR are related to multiple factors rather than biology itself. And therefore, we need to do a lot of pre-processing to make it suitable for further modeling. So I should say that clean modalities like CT or even PET, they are far more friendly for radiomics. Mm-hmm. And as far as anatomical areas concerns, I think the breast, the lung, mainly mainly cancers that they have a very high prevalence. Those are the ones that are already being tested and exploited.
Yes. Okay. Well, I think we have no more questions coming in at this moment. I do see a lot of very positive reactions. So I also think this was a very interesting webinar. So Nickolas, I would like to thank you on behalf of the USOMI and all the attendees. And of course, I would also like to wish you a Merry Christmas and happy holidays, let's say. So thank you very much. And yes, well, I wish you good luck and a lot of success with the further research.
Thank you for having me here. It was a very nice experience for me as well to interact with you guys and share experiences and different comments.
Okay, likewise. Thank you and have a very good evening.
You too.
Okay, bye-bye.